In this video, we'll learn about the primary beam of a single-dish antenna and how this relates to the primary beam and field of view of an interferometer.
As we learned in the Introduction to Interferometry video, each pair of antennas in an interferometer is sensitive to structure in the sky whose size scale depends on the distance between the antennas, called the baseline. Longer baselines are sensitive to smaller scale structures in the sky, while shorter baselines are sensitive to larger scale structures. Thus, the angular resolution of an interferometer depends on the longest baselines, while the largest structures that an interferometer can detect, called the maximum recoverable scale, depends on the shortest baselines of the interferometer.
But there is another size scale that must be accounted for when dealing with an interferometer, and that is the response of each individual antenna to radiation from the sky. Each antenna is only sensitive to a finite area of sky, with the greatest sensitivity along the axis of the antenna and gradually decreasing away from the axis. This is referred to as the antenna beam.
What does this mean and why does it matter? Recall your undergraduate physics labs where you shone a laser through a slit. Because of the wave nature of light, the laser is diffracted as it passes through the slit, forming a characteristic pattern of peaks and troughs on the screen. The width of the peaks depends directly on the wavelength of light, and inversely on the diameter of the slit. When the slit is narrow, the peaks broaden, but when the slit is wider, the peaks get narrower. Similarly, if we keep the slit the same size, then a longer wavelength of light broadens the peaks, while a shorter wavelength narrows them.
If we replace the slit with a circular hole, the pattern looks like this, with a bright circular central peak, or lobe, with faint circular rings called side lobes surrounding the central peak. Most of the power from the laser falls within the bright central lobe, with a fraction of the power diffracted into the side lobes.
How does this relate to ALMA? Each antenna can be thought of as a circular hole with size the diameter of the antenna. Thanks to a principle called the antenna reciprocity theorem, a receiver, the ALMA antenna, is exactly analogous to a transmitter, the laser in this case, but in reverse. In the laser slit experiment, the laser shines on the hole, sending power outwards in the diffraction pattern. For an antenna, the path is in reverse, with the receiver in the place of the laser, and the antenna dish forming the circular hole. The incoming radio signals are diffracted by the receiving antenna in the same way that the outgoing laser light is diffracted by the transmitting slit.
Unlike the laser shining on the circular hole, however, the antenna optics can be designed to greatly suppress the side lobes so that only a very tiny fraction of the power goes into them. For most practical purposes, when dealing with ALMA data, we can ignore the side lobes completely and concentrate just on that central lobe. This central lobe is the antenna beam.
Even within the central lobe, however, the sensitivity to the sky is not uniform. It's most sensitive directly along the axis of the antenna, but decreases with increasing distance from the axis. At a certain distance away from the axis, the antenna is only half as sensitive as it is toward the axis. The width of the beam at this point is often referred to as the full width at half maximum, or FWHM of the beam, and it is proportional to lambda over d, where lambda is the wavelength of electromagnetic radiation, and d is the diameter of the antenna.
We have just been talking about a single antenna. For an interferometer, the combined beam patterns of all the antennas form the response of the array, called the primary beam, or field of view. For a homogeneous array, like the ALMA 12-meter array, or the 7-meter array, where all the antennas have the same diameter and optics, the primary beam of the array is identical to the antenna beam, and is simply expressed as being a function of lambda over d, where d is the diameter of the antennas. For heterogeneous arrays, where antennas can have different sizes, the primary beam is calculated using a complex product of antenna voltage patterns, and is hence much more complicated. In this video, we will only be dealing with homogeneous arrays.
Why is the primary beam of the array important? Let's look back at our laser slit experiment for a moment. When we introduce a second slit, we now see the interference pattern from the two slits, but the interference pattern is still constrained by the diffraction pattern from each slit. Similarly, in an interferometer, the interference pattern between each pair of antennas is constrained by the primary beam.
In practice, this means that an interferometer is only sensitive to structure within the primary beam of the array, what we call the field of view. As we've noted before, the sensitivity also changes within the field of view. The array is most sensitive to structure in the center of the field of view, and less sensitive as you move away from the center.
Let's look at an example by simulating an ALMA observation of molecular clouds in a galaxy such as this one. The full width half maximum of the primary beam of the array at a certain receiver band would cover an area roughly shown by the circle on this image. The resultant image of our simulated observation would look like this. Because the sensitivity drops as we move away from the axis of the primary beam, notice how the galaxy fades away as you move away from the center of the image.
If we were only interested in what's happening near the axis of the primary beam, which is often called the phase center, then we might be quite satisfied with this image, and we'd be finished. But if we're interested in the molecular clouds we see away from the center, then we run into a problem. Let's say we want to measure the integrated intensities of the clouds we've detected in this image in order to estimate the mass of the clouds. This is a simulation, so we know what the true sky looks like. Let's compare the integrated intensities we measure from the observed or simulated map with the true values by plotting the ratio of observed to true flux densities as a function of the distance away from the phase center. Close to the phase center, the observed value is very similar to the true value, but as we move outward, the observed values get progressively smaller because of the primary beam response, shown here.
We can account for the reduced sensitivity by correcting the observed map for the primary beam, essentially dividing the map by the primary beam response. The primary beam corrected map now looks much closer to the true sky image, and you can see that when we compare the integrated intensity measured in the corrected image with the true value. But only to a point. Once you get well beyond the full width half maximum, we are dividing by very small numbers. So any noise in the image, which is relatively constant across the observed image, will be greatly magnified. In practice, we simply discard anything beyond where the primary beam is too weak.
What if we were interested in what's happening outside this region? In that case, we might want to make a mosaic, which we'll explore in another video.
We've just learned about the primary beam and field of view of an interferometer. You might want to check out our other videos, some of which are shown here. Happy observing!